In this video, I'm going to talk a little bit about the homonuclear diatomic molecule. So homo means same, nuclear, talking about the nucleus. And so we're talking about molecules that have the same atoms in it, and diatomic means that it's two of them. And so it's the things like H2 and helium-2 and lithium-2 and N2 and O2 and those kinds of things. And like I said, we will, in the previous video, we will see sort of why something like helium-2 doesn't exist, or at least not, outside of some very, very sort of particular and extreme conditions. But anyway, so the first thing to talk about, so this guarana and unguarana here, which will be showing up in our molecular orbitals. So we have the sigma G and the pi G, and these could also have stars by them for guarana, and then the sigma U and pi U, and those can also have stars by them if they're anti-bonding. And so that just means that they're symmetric G or anti-symmetric U with respect to an inversion. And so this is an illustration here of what these look like. So if we go down here, so our sigma G and our pi G, so the sigma bond is obviously the sort of single bond, the bond where the two things that are sort of pointing right at each other. So like a p orbital and another p orbital, or a p orbital and an s orbital, or something like that. And so this we can see is symmetric to inversion, because if you sort of inverted this, so you took everything and just sort of moved it to the opposite side, so just switch places on the opposite side for everything, you would just get the same thing back again. And so the same thing for this this pi G. So we're taking sort of something that's up here and we move it down to there, while this one gets moved up there. Something up here is moved down to here. And so we're just inverting everything sort of across the origin. So I guess over here, an inversion would actually look more like we're taking something up here and moving it down to right there, where something up here is getting moved down to right there. Then we have the unguarana, which means is anti-symmetric to inversion. So if we took something like right here on this side and moved it down to here, see, we're now we're switching from blue to red. So the red and the blues will all sort of switch places. And so you can assign negative and positive to whichever color you want, but the idea is that the sign is changing. So if red is negative and blue is positive, when we do an inversion, the positive will get moved over here and the negative over here. And so we can see that with these anti-bonding orbitals as well. And so the pi U star and the sigma U star, we can see how those, if we sort of invert everything across the origin, then those would end up being, switching the sign. And then the pi G star and the sigma G star are symmetric with inversion, because if you took something like from right here, for instance, and moved it down to right here, it would maintain the same sign. And so the other thing to notice too is that as we go up this this table here, we're increasing in energy. So these bonding orbitals, so these sigma G and pi G are sort of the lowest energy, so those are the most stable. Then the pi U and sigma U are sort of the next up. Then we have the anti-bonding orbitals, which are sort of the higher energy, and so those are less stable. And in fact, they're disfavored compared to the atomic orbitals, and that's why they're anti-bonding. All right, so another thing to think about when we are talking about our molecular orbitals is that if we have molecular orbitals that are close enough in energy, then we get orbital overlap. And what that does is, and what we can see here in this figure here, is that it takes these sort of lower orbitals right here and moves them down to a lower energy, where it takes these two upper ones up here, so the ones in the kind of dark red, and they get moved up to this higher energy here. And so we see that's why this sigma here, which is what we would expect, this sigma g, because that is the lowest energy, that is what we have up here, is lower energy than these pi, or these pi u here. So the pi u, which is this up here, that's higher energy. So we would expect that to be higher than the sigma g, but because of this orbital mixing, these sigma g's right here are actually getting pushed up higher than these pi u's here, and so we end up with this kind of being above those for some of our elements here. And so yeah, the overall thing to notice is that these sort of two upper ones, this sigma u and this sigma g, are sort of getting pushed upward, while this sigma u star and this sigma g here are getting lowered in energy. So in the above, so yeah, the molecular orbitals have the same symmetry, the sigma G2s and sigma G2p. So they have the same symmetry, which is the infinite rotation and inversion. And so they interact and they lower the energy of the sigma G2s orbital and increase the energy of the sigma G2p orbital. So the same is true of the two antibonding orbitals. We have then for the 2s and the 2pz orbitals, so this is our molecular orbital wave function. And so we have here, so the pluses on top are when it's the bonding, the negatives on bottom are when it's the anti-bonding. And for our homonuclear molecules, which means that we're bringing these same atoms into to bond into the molecule, then the C1 and C2 will be equal, and the C3 and C4 will be equal. And so for the sigma G2s and the sigma U star 2s, the C1 and C2 will be greater than the C3 and C4, because up here the 2s orbitals here are going to be sort of contributing more to the bond. So those are the 2sa and the 2sb. So those are contributing more to this bond right here, this sort of sigma s and sigma s star, or the sigma g and sigma u star. And so those are getting more of these first two terms in the linear combination here. And then it's the opposite for the sigma g, the 2p, and the sigma u star for the 2p, which are these two up here. This one, well, I guess we should be looking at this one right here and this one right here. So those will have more contribution from these second two terms right here. And so we can actually look at the trend in energies here for the sort of first row of the periodic table. So we have the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon here. And so if we look at this right here, so on this side, on the left side of the periodic table, this pi is lower than the sigma, but when we get to what I have here in the red box between N2 and O2, we see that that switches, and now we have the sigma and 2p, or the sigma lower in energy than the 2p. And the reason for that is if we look at the gap between these two s's right here and these two p's right here, it gets larger as we go from left to right. So as we go down here, the gap in the energies becomes larger. And so we get less and less interaction between the 2s and 2p. And I mentioned in the last video, it's around 12 electron volts that the interaction kind of goes away. And so we can actually look at this over here. So this is the atomic orbital ionization energies, which is kind of a measure of the energy of those orbitals. And so if we look here, so our boron, the difference in energy between the 2s and the 2p, so I wrote in the differences in the energies here. So we have 5.7 and 8.8. Then nitrogen is 12.4, so it's kind of right on the cusp there. So the nitrogen still has the pi orbitals here below the sigma orbital, but it's kind of right on the cusp. But then when we get to oxygen, we are at 16.4, a difference of 16.4 electron volts. And so there is little to no interaction. And so that switches it so that we have the sigma now lower than those pi bonds there. And that will remain true for the fluorine and for the neon here. And so that's kind of the first thing we can sort of see on this table. The next is kind of how these electrons are being filled in. So we see with lithium, the sort of the dilithium here, we have a bonding molecular orbital that's filled there. When we get to the beryllium, we have a bonding and an antibonding. And so the beryllium will not actually bond to itself. You will not actually find these diberyllium molecules like this, because this antibonding cancels out this bonding. And so we actually see that too with the neon here, but we see it up here because it has more electrons, that we have these 3 antibonding here and these 3 bonding. So the 3 antibonding are canceling out the bonding, and so you will not find di-neon molecules. And the same argument could be made for helium, and all of the noble gases have this, where it has equal number of antibonding and bonding, and so the bonding order will be 0. And so boron, though, we see has kind of the same thing going on as oxygen does, where we have these 2 lone electrons here. Well, it's a little bit different because these are 2 lone electrons in the bonding, where these are 2 lone electrons in the antibonding. But this will sort of give us another double bond right here, and this will sort of remove a pi bond, so that it brings us down from kind of these 3 bonds here down to a bond order of 2. So we can kind of see that in this figure right here. So as nuclear charge Z increases from boron to fluorine, the difference in energy between the 2s and 2p, as I said, increases, resulting in a less orbital mixing. And so yeah, that's just kind of what I already said. And so we can look at a few of these in some more detail. So we can look at our helium here. And so this is the sort of molecular orbital electron configuration right here. So we are bringing these 2 atomic orbitals from one helium and 2 atomic orbitals from another helium, and we generate these sigma and sigma star right here. So that's the sigma G with the 2 telling us how many electrons there are, and the sigma U 2 star telling us how many electrons there are in the antibonding. And we see that this antibonding will cancel out, this antibonding here will cancel out the bonding down there, and so the helium will not bond to itself, and so that's why it's only ever really found, except in very sort of particular sort of experimental situations, you can sort of form helium molecules, but we won't be getting into that here. So we can look at C2, so just 2 carbons. So the Lewis structure of that would be something like C double bond, and then it has sort of these 2 lone electrons on the outside here. So that's what C2 would look like. And you can kind of generate this in, once again, sort of experimental situations in the gas phase, but these single electrons want to partner up with something, and so they will tend to bond to something else. So one of the interesting things about this, though, so yeah, like I said, we can have this in the gas phase, and it has this bond distance of 132. But the thing to notice is that this sigma here, because of the 2s and 2p interactions, is increased, and so the two bonds between these carbons are pi bonds. So there is no sigma bond in this species right here. It is so it's unusual for having two pi bonds and no sigma bond for the carbon there. So then the nitrogen here. So once again, we have our molecular orbital configuration. So we actually looked at this one in the previous video. This is just the same figure. So we have the filled bonding and filled anti-bonding canceling each other out. This filled bonding and filled anti-bonding for the 2s canceling each other out. And then we have these three filled bonding orbitals. And so that's why nitrogen has a triple bond. So nitrogen is like this. And this is, a very strong bond. As a matter of fact, there are, techniques that require, like gas chromatography, like high pressure chromatography and things like that, where you use nitrogen because it's so stable, because this triple bond is so strong here. If you can't really, I mean, it's kind of easier to get than helium, and so sometimes you will use nitrogen gas in those situations because it's very stable, which is why, even though our atmosphere is like 70% nitrogen, it's very hard for organisms to actually use nitrogen. And, there are certain plants and so forth that can do nitrogen fixing, that can sort of take this out of the air and sort of turn it into usable nitrogen. But for the most part, we would think of it, at least for ourselves anyway, as being very inert in the air. So it's very stable. So the oxygen here, we have our molecular orbital. Configuration here. So we see we have these two anti-bonding pi bonds here that just have a single electron in each of them. And so, yeah, we talked about this in the previous video. So we have this sigma bond here, these two pi bonds here, but then these two single electrons, which effectively cancel out one of these pi bonds. And so oxygen is, in fact, something that has two bonds, so it's a double bound molecule. Because it has these two lone electrons, which will, because of Hund's rules, they will want to be in the same sort of spin configuration. You actually get sort of a net spin on this, and that makes oxygen actually paramagnetic, and so it can actually be affected by a magnetic field. So here are just some of the oxygen species, some of the ionic oxygen species. So the O2 with one electron removed, we have this bond order of 2.5, because if we say removed this, now we have this sigma bond, we have this pi bond, and we have kind of half of this other pi bond here. And so that's a bond order of 2.5. And so that we see that reduces the internuclear distance, because that increased bond order is going to be stronger, and so it's going to hold the atoms closer together. So we have the O2, which is just the oxygen, is the bond order of 2, and it's about 120 picometers from each other, the two nuclei. So if we have superoxide, which adds another electron, so we might add another electron right there. And so that brings us down to a bond order of 1.5, and we see that causes the bond to increase in length. And then the peroxide here, which would be kind of like adding another electron right here, and so we're down to just this single bond right here, so a bond order of 1, and this has this particularly long bond length here, so internuclear distance. And so we also have the fluorine here. We have the molecular orbital configuration right here. And so we see that this is just going to be a single bond because these two anti-bonds will cancel out these two bonds right here. So the Lewis structure for fluorine is something like this. And so we'll put our lone pairs around here, which are turned back into lone pairs because of these anti-bonding orbitals here. And so we see we have 2, 4, 6, 8, 10, 12 electrons in the lone pairs. And so that is because we have the 2, 4, 6, 8, and then the 12 right here from our antibonds there. So we can look at the bond distance of homonuclear diatomic molecules, and so we see that as we go down to the nitrogen, the bond distance becomes smaller and smaller. But then as we go up these oxygen species and then even up to F2, the bond distance becomes larger, and that's because we have these reduced bond orders. Because we're losing those triple bonds. The nitrogen has that triple bond, that bond order of 3, and so those kind of hold things tight to each other. Then so the atomic radius we see just sort of goes down, as is the trend of the periodic table. As you go from left to right, the atomic radius goes down. And that's because we have the same number of shells in each of these. So we have the 1s2, the 2s2, and then the 2p, and then I guess we can put n as we go down, so n going up by 1 as we go down. So we have the same number of these shells here, but the z, or the positive charge, so the positive charge is increasing by +1 each time we go down this, and so it's sort of pulling in the electrons closer and closer to the nucleus because of the increased sort of positive charge from it. But yeah, anyway, that was what I wanted to talk about here for these homonuclear diatomic molecules. As usual, these lecture notes will be linked to in the description down below. If you wanted to look at some of these figures in a little bit more detail, or look at them a little bit slower on your own. But yeah, I hope you found this video useful, and I will see you in the next one.